Hey, what's up, guys? Okay, so in this video, that we are going to show the following, right? So, if previously we have showed that the cyclic prime powers of P is a prime. Sorry, let's say R prime. So Z to the PK cross is a cyclic group. So basically, what this mean is, all this means is that there's a cyclic, there's a primitive roots. Okay. And if we know that in this video that we are easy to prove that 2p to the k, this also is a cyclic group. So basically, there is a primitive roots. So there is a primitive roots. Okay, so in order to prove it, we are subject to the following lemma. So we should appeal to the following lemma. Okay, so this lemma says that if let's say I pick G is a primitive roots of P to the K, then if G is odd, then G will be the primitive roots of P 2P to the K. So G will be the primitive roots of 2P. Okay, and if G is even, then obviously that the G plus P to the K will be odd. If G is even and G is primitive roots of P to the K, as this condition, then G plus P to the K will be odd, and also be the primitive roots of 2pk. Okay, so this is the main theorem that we are going to prove. If we have these two, then obviously that we show that there's a primitive roots of 2pk. Okay, so let's quickly go through proof. So this proof is somehow trivial. Okay, so in the first part that if G is primitive roots, so that means of pk, that means that G to the phi of pk is 1 mod pk. So let's see, so let's say S. Let's say that S to be the primitive roots of, okay, so let's say S to be order of G over 2pk. Okay, so that means that GS is 1 mod 2pk. Obviously that from here and here that we know that S is greater or equal to 5pk, right? Because that you increase here, or increase the modular number, that the order should be higher. Okay, so S is greater or equal to this. But since S is uh right, so but the problem is that this S, right? Any S need to be less or equal to phi to the 2pk. Oh, sorry, phi to the 2pk. And the phi to the 2pk is phi of 2 times phi of pk, which is still phi of pk. Right, so this force that S must be phi to the pk. Okay, so notice that the reason that we can find the order because G is odd. So I should say since G is odd, so that means that the G is coprime to P to the power K. So that means that the order exists, and since the order exists, that order must be greater or equal to phi to the pk by the definition, also less than the phi of 2pk using the definition of the primitive roots. Then this implies that x must be the maximum order. So this shows that G is a primitive roots of 2 times P to the K. Okay, so the second one that is trivial. it's almost trivial by just seeing if G is even, that means that G plus PK is odd. So that means that G plus PK is to 2P to the K is 1, right? So we can consider S to be the order of this guy, G plus PK to the S. It should be 1 mod 2PK. And then due to a similar reason, right? Due to a similar reason that since G is even and the primitive roots, it's trivial to show that in order for this equation to hold, that the S must be the same as phi to the 2PK, phi PK. So the proof is almost the same, just using the probably basically using the first one. Okay, so this is the proof, and see you guys next videos.